Hello everyone, this is Andrea Del Prete and welcome to my talk for GAP Season 2. Today I will talk about a generalization of a Jenkins-Herring theorem in free manifold emitting a non-singular Killing vector field. This is a joint work with my two PhD advisors, José Miguel Manzano from University of Jaén and Barbara Nelli from University of L'Aquila. Let us begin with some history about the results that inspired this work. In 1966, Jenkins and Serrin introduced what after them was called the Jenkins-Serrin problem. They considered a bounded domain of the plane, whose boundary consists of straight line segments and convex arcs, and gives necessary and sufficient conditions on the length of described polygons, which guarantee the existence and uniqueness of minimal solution to the Dirichlet problem with possibly infinite boundary values. In the last 20 years, more or less, due to the interest in Thurston geometries, there has been a desire to extend what was known about constant curvature surfaces theory in the Euclidean space to as many homogeneous manifolds as possible. For what concerned the Jenkins-Herring problem, the first result was achieved by Nelly and Rosenberg in the cross product H2 cross R. After them, Pinheiro and Macei Rodriguez Rosenberg proved the result in any product space and cross R where M is a Riemannian surface. Yuns proved it for the case of the universal cover of the special linear group, and Nguyen proved it for the three-dimensional solvable group. It's interesting to notice that despite the difference and the complexity of the ambient spaces where the problem has been solved, the necessary and sufficient conditions that guarantees the existence and uniqueness of solution are always the same. Furthermore, the proofs of all these results share the same outline. This can be resumed in the following step. In their work, they prove the compactness theorem and the monotone convergence theorem and use them to study the convergence of a sequence of minimal graphs whose boundary value convert to the desired one. To do so, they prove the existence of upper and lower barriers that are necessary to apply the compactness theorem, and then use a flux argument to study the shape of the divergent set of such sequence. In our work, what we do is to generalize this technique to the more general case of three-dimensional Riemannian manifolds, which emit a non-singular Killing vector field and that can be described as a Killing submersion over a Riemannian surface M. Before facing the problem, we need to see some definitions and give some features of the ambient spaces where we are going to work. So we consider a three-dimensional manifold E and a Riemannian surface M, both connected and orientable, and we denote by Xi a non-singular Killing vector field of E, that is, Xi satisfies these two properties. Then we can define a Killing submersion as a Riemannian submersion whose fibers are the integral curve of the Killing field. In every Killing submersion, we can define two characteristic functions: the Killing length, that is the norm of the Killing vector field, and the bundle curvature, that is defined by this equation, and in some way it describes the metric of the ambient space E. Since Xi is Killing, it has an associated one-parameter group of isometries of E that is called vertical translation, and we can notice that by definition mu and tau are invariant with respect to this group, so they are constant along the fibers, and we can think them as functions of the surface M. Another important property of the Killing submersions is that the horizontal frame, that is the frame that is orthogonal to the Killing vector field, is integrable whenever the bundle curvature is zero. The last property we want to point out is that the geodesic fibers correspond to the critical point of the Killing length. This is interesting because if we take a geodesic in M and we consider the pre-image through P, the surface we get it is not necessarily a minimal surface. The most important result about Killing submersion is due to Lerma and Manzano. They prove that if M is simply connected, then E is simply connected, and it is fully described by the choice of M, tau, and mu. They indeed prove that if M is diffeomorphic to an open subset of the plane, then E has to be diffeomorphic to the product space D cross R, and the projection is the trivial one. If M is a sphere, then depending on the value of this integral, A could be the product space S2 cross R or the free sphere, and in the last case, the projection is the off vibration. They also prove that if E and M are not simply connected, then the space we get is a quotient of one of these spaces that we already seen. But why Killing submersions are so interesting? Well, for example, every simply connected homogeneous tree manifold is described as a Killing submersion. We can use the classification with respect to the dimension of the symmetry group to understand it. Indeed, if the dimension of the symmetry group is 6, what we get are the space forms. In all these cases, the bundle curvature is 0, and the sectional curvature of the base surface is constant, and in the case of the Euclidean space and the sphere, the Kinley length is constant equal to 1. In the case of the hyperbolic space, the Kinley length is a function of the hyperbolic plane. When the dimension of the isometry group is 4, we get a two-parameter family known as I kappa tau spaces, where the constant parameters kappa and tau satisfy this inequality, although we get a space form. In this case, the tau is the bundle curvature of the Killing submersion, the Killing length is constantly equal to 1, and kappa denotes the constant sectional curvature of the base surface that is simply connected, and so it's unique. These spaces became famous because they contain all the Thurston geometries except for the hyperbolic space and the solvable group. The first one because, as we said, it has a non-constant Killing length, and the second one because its isometry group has dimension 3. The last case is when the isometry group has dimension 3, and in this case, Milnor proved that each space with this property is isometric to a metric Lie group endowed with a left invariant metric where every right invariant vector field is Killing. And it is not difficult for each case to compute the value of tau, the value of mu, and the metric of the of the base surface. Another example of Killing submersion are warped product with one-dimensional figure. Warped product are product manifold M cross R with M Riemannian surface, whose metric is a deformed metric through a warping function f that is a positive function of the surface M. The Killing submersion in this case is the trivial one from the product space onto M, and the bundle curvature is constantly 0, and the Killing length is exactly the warping function. And last but not least, Killing submersion theory is important because it gives another description of homogeneous manifold with dimension group at least 4. We know indeed that when the dimension of the symmetry group is at least 4, the manifold has the rotational isometry and the composition of rotation and the translation. So we can construct the Killing submersion whose fibers are exactly the integral curve of those Killing fields. The easiest example to compute is describe the Euclidean space with respect to the rotation above a straight line. So we have that the Euclidean space without the straight line L is isometric to a quotient of the Killing submersion E characterized by the base surface that is the Euclidean half-plane, the bundle curvature is 0, and the Killing length is defined as the distance of a point of M to its boundary. In this case, we need to take a quotient because the integral curve of this Killing vector field are circles centered in the whose center is in the line L. So the fibers has to be compact, and we need to take the quotient. In general, if we have a three-dimensional manifold emitting a non-singular Killing vector field, if the one parameter isometry group associated to the Killing vector field acts freely and properly on the manifold, then this manifold has a natural representation as a Killing submersion over a certain Riemannian surface. Our interest is to study minimal surfaces embedded in a three-dimensional manifold with a Killing vector field. So we consider a general Killing submersion. We denote by sigma an orientable inverted surface in E, and we denote by n its unit normal vector field. We can define the angular function of sigma as the product of its normal vector field and the Killing vector field C. So we have that sigma is vertical in every point and is horizontal. That is, sigma is vertical in every point where the angle function is 0. So we have that if the angle function is always 0, what we get is that sigma is a vertical cylinder. Otherwise, when the angle function is nowhere 0, we define sigma to be a multigraph. For what concerns the vertical cylinder, we compute its mean curvature equation, and we consider gamma to be a regular curve, and we define sigma, the vertical cylinder sigma, to be the pre-image of gamma for P. So its mean curvature equation is given by this equation, and it depends on the Killing length and the geodesic curvature of gamma computed in the conformal metric with conformal parameter mu. So this means that minimal vertical cylinders correspond to geodesic of M computed with this conformal metric. Due to the importance of this conformal metric, we will use the prefix mu to indicate the corresponding terms computed with respect to such metric. Notice that radial mu geodesic at some point P of M produce an open book decomposition of a neighborhood of P. So the corresponding minimal cylinders produce an open book decomposition by minimal surfaces of the neighbor of the fiber above P. But our interest is to solve the Alderiche problem, so we need to give a meaningful definition of what a graph is. So we take an open subset U of M. We take a smooth section F0 over U, and we take a phyto function over U that we call U. So we can define the graph of U with respect to F0 as the deformed section through through the vertical translation above each point. In their work, Lerma and Manzano compute the mean curvature of any killing graph, and it is given by this equation that is in the divergent form. In our work, what we did is to prove that if the open subset is relatively compact, we can assume F0 to be minimal. Now that we know the setting, we can approach the problem, and we start defining the features of the domains where we want to solve it. So we say that an open, connected, and relatively compact domain omega of M is a Jenkins-Ring domain if its boundary is piecewise regular and consists of mugeodesic arcs and mugeodesic closed curves denoted by the letter A and B, and regular curves denoted by the letter C, which have a non-negative mugeodesic curvature with respect to the inner normal vector. We call corner set the set of intersection points of all this curve, and we say that a Jenkins-Ring domain is admissible if it satisfies these two conditions. The first one is a necessary condition that followed by an application of the flux argument, which we'll see later. And the second condition is a condition that we need to solve the problem whenever the set of regular curves is empty. Notice that we are not making any assumption on the topology of omega or M. If omega is an admissible Jenkins-Ring domain, we can define the Jenkins-Ring problem as the following Dirichlet problem, where the Fi's are continuous functions over the regular curves. Notice that the parts of the boundary on which the solution diverges must be mugeodesics because in their neighborhood, the solution is becoming vertical, and it can be shown that it is asymptotically tangent to a minimal vertical cylinder. To state the theorem, we also need to define what is a polygon in this setting admitting non-simply connected cases. So, given a set of points V, we define a mugeodesic polygon P with vertices in V as the set of mugeodesic arcs denoted by the small gamma and mugeodesic Jordan curves denoted by the big gamma, such that the union of all these curves is the boundary of a relatively compact and connected subset of M. Each point in the vertex set is the endpoint of exactly two mugeodesic arcs in small gamma, and the last hypothesis is that all these mugeodesics do not intersect in interior points. We can see in this picture an example of a simply connected surface whose matrix allows the existence of non-simply connected mu polygon. Now we have all the ingredients to state the Jenkins-Ring theorem. So, given omega an admissible Jenkins-Ring domain, we denote for all mu polygons P where vertices are among the endpoints of the mugeodesic arcs AI and Vj, we denote alpha by alpha the total mu length of all the AI contained in P, by beta the total mu length of all the Vi contained in P, and by gamma the mu perimeter of P. So, if the family of regular curve is not empty, the solution to the Jenkins-Ring problem exists if and only if these two equations are satisfied for all mu polygons contained in omega. If the family of regular curves is empty, we have that the solution exists if the two equations above are satisfied for all the mu polygons that are different from the boundary of omega, and when the mu polygon considered is exactly the boundary of omega, we have that the two lengths reach the equality. In the first case, the solution when exists is unique. In the second one, when the solution exists, it is unique up to vertical translation. So following the original outline, the very first result we need to prove is the compactness theorem, we state that if a sequence is uniformly bounded in a domain, then there exists a subsequence which converts to a solution of minimal surface equation in such domain. These results rely on a series of gradient estimates, which depends on the estimate of the area element, and the Ascoli-Arzelà theorem. What we did is to use a result of Rosenberg-Swan-Tubiana, which guarantees a bound for the second fundamental form of a stable surface of constant mean curvature, to prove that the area element of a minimal Killing graph over a relatively compact domain omega that admits a C0 bound is bounded in each point of omega. After it, we extend an argument of Yuns and Sprug to obtain a C1 estimate from the previous one. And finally, using the Ledizhenskaya-Urasheva theory, the Schauder theory, and standard elliptic PD arguments, we obtain from the C1 estimate a CK estimate for all K natural. As a consequence of the compactness theorem, we prove also the monotone convergence theorem, which states that a non-decreasing sequence of solution to the minimal surface equation in omega converges in an open subset U of omega in the CK topology, that the open subset is called convergent set, and diverges uniformly to plus infinity in its complementary, that is called divergent set. So to apply these two results, what we need now is to prove the existence of solution to the Dirichlet problem with finite boundary values and the existence of barriers. For what concerns the Dirichlet problem, we solve first the simply connected case and then extended the result to the more general one. It is not difficult to see that the minimal surface equation we described before in a divergent form is a quasi-linear elliptic PDE. So the classical results of this theory guarantee that any simply connected domain omega with C2 boundary admits a smooth minimal solution for every bounded continuous boundary value. So we need to focus in the discontinuous case and also allowing the presence of vertices in the boundary of omega. To do so, we use a technique used first by Nietzsche. So we consider omega with boundary piecewise C2 and piecewise continuous function on the boundary, and we denote by V the set of discontinuity points. We call Nietzsche contour the continuous curve that is the image of F together with the vertical fiber above the discontinuity point that makes such curve continuous. We also call Nietzsche graph the C2 extension of a Nietzsche 2 contour in the interior of the domain. We say that a Nietzsche contour is admissible if the mu-geodesic curvature of the boundary of the domain where the function is defined is non-negative with respect to the inner normal, and also if the interior angle at each vertex is at most p. This condition of admissibility allow us to use the Mix-Yau theorem, which guarantees the existence of a minimal surface with boundary any Nietzsche contour that is admissible. So what is left to prove is that the Mix-Yau solution for the Nietzsche contour is indeed a Killing graph over the interior of omega. The proof of this theorem is a consequence of a generalization of the maximum principle to Nietzsche graph, whose proof is omitted. But the idea of how to prove this theorem is quite simple. So we consider as the Nietzsche contour the Jordan curve in this first picture. In this case, we have only one discontinuity point, but the same argument can be easily applied to the more general case. What we do is to slightly deform the Nietzsche contour in a neighbor of the vertical fiber in order to obtain a Jordan curve, or better, an increasing sequence of Jordan curves, which converges to the initial one, that are the image of continuous functions. So we consider the sequence of solution with such boundary values that are unique and that is an increasing sequence for the maximum principle. Now we can apply the monotone convergence theorem using as upper barrier the Mix-Yau solution. And what we have is that this sequence of minimal solution has a limit that is a Killing graph whose boundary is exactly the Nietzsche contour we want. Repeating the same outline from above, we have that the Mix-Yau solution is between two Killing graphs that have the same boundary. So the maximum principle implies the result. Once proved existence in the simply connected case, we use the Perron process to extend the result and prove the existence of a bounded minimal Killing graph over admissible Jenkins-Herring domain. So we recall that given the Dirichlet problem P omega f, a continuous function U is a subsolution for the problem P omega f if it is smaller or equal than m omega tilde u, where for any small closed disk omega tilde, where m omega tilde u is this function defined here. And furthermore, if in the boundary of omega, the function u is smaller or equal than f. Changing the inequalities, we have the definition of a super solution. Obviously, if u is a solution of the problem P omega f, then it's also a subsolution and a super solution. So the Perron process states that given an open domain omega of M and a piecewise continuous function f, if the problem omega of f admits a super solution phi, we call S of phi the set of super solutions smaller than phi. Then, if S of phi is not empty, its two primum is defined for all the points in omega, and it is a C2 function that satisfies the minimal equation. Furthermore, if for any point of the boundary of omega we can construct an upper and a lower barrier for the problem, then we have that such solution extend continuously up to the boundary. Applying the Perron process to solve the theorem, we need to verify these two items. But the first one is trivially satisfied, since we already proved that for any relatively compact domain of M, there exists a minimal section above it, and translating up and down this section, we can find a super solution phi, and we can see that this set S of phi is not empty. For what concerns this second item, the existence of upper and lower barrier for any point of the boundary will be guaranteed by the existence of shared tight surfaces over small triangles. The construction of local barriers is the key result of our work, and the technique used to prove it is different from all the previous results. In fact, in previous works, such surfaces were either found explicitly, as in the Euclidean case, or their existence was proved using the Douglas principle. The use of the Douglas principle allowed to construct shared surfaces on triangles of any size, but this technique is not always applicable, as in the case, for example, of the Heisenberg proof. What we do, however, is to conveniently use the Mix-Yau theorem we stated before to find a sequence of uniform barriers over any compact subset of the triangle. So we consider a sufficiently small geodesic triangle theory, where for small we mean that it is contained in a larger triangle T tilde, as in the figure, which which is itself contained in the intersection of the normal neighborhood of its vertices. In this way, the in T tilde, there is an open book decomposition through mu geodesic with binding Q tilde 3 and Q tilde 2. We also need the interior angle of the triangle T to be at most pi. In this setting, we want to find a minimal surface that has zero boundary value on the side L2 and L3 and that diverges to plus infinity approaching the side L1. So we start considering a sequence of minimal Killing graph that has these boundary values. Notice that this sequence using the maximum principle is strictly increasing. The idea so is to use the monotone convergence theorem. To do so, we need to find uniformate estimate for any compact subset of T. To that purpose, we build the following sequence of minimal surfaces using the Mixed-Yau theorem. So we fix the triangle T at H0 and we consider the free manifold which has as boundary the triangle T lifted to H1 and the vertical cylinders above the side of T. Such manifold satisfy the hypothesis of the Mixed-Yau theorem, and so there exists an area minimizing surface that has as boundary this pink curve, this black one. By recurrence, we can construct a sequence of minimal surfaces that we denote by dn in this way. We consider as the ambient manifold as three manifold, the three manifold that has as boundary the triangle T lifted to 8n, the Mixed-Yau solution in the previous item, that is dn minus 1, and the part of the vertical cylinders above L1, L2, and L3 that make this boundary homeomorphic to a sphere. Notice that again, in this case, the maximum principle implies two things. Each decay is above any un for any k and n natural, and in the subset of T where both decay and decay plus 1 are Killing graph above this domain, decay plus 1 is below decay. We also notice that the projection of this sequence through P is a steadily increasing sequence of compact subset of T. If this sequence is an exhaustion, it follows that for any n, un has an upper bound on any compact subset of T. So to prove that this sequence is an exhaustion, we need to consider a new sequence of stable minimal surfaces given by translating down each decay of a quantity k over 2. So if the limit of this new sequence is the vertical cylinder above L1, we have done. Because it means that for any compact inside of T, there exists a K such that the projection of the K covers this domain. So we assume by contradiction that its limit, the infinity, whose boundary consists of the fibers above Q3 and Q2, is not the vertical cylinder above L1. Hence, a part of the boundary of its projection should be something like this red curve. Here we use the open book decomposition by mu geodesics with binding Q2 tilde, and we denote by gamma the first mu geodesic that has a contact point in P with the red curve. If the cylinder above gamma touches the infinity at an interior point, the maximum principle implies that the two surfaces must coincide, but this cannot happen since a part of gamma lies outside T. So we assume that the infinity and the cylinder above gamma are asymptotically tangent along the fiber above P. And to solve this last case, we have to study the limit of another sequence of stable minimal surfaces. We consider a sequence of points Pn in the infinity whose distance converges from distance from the cylinder above gamma converges to zero. This means that the projection of this point is a sequence that converges to P. And the new sequence of surfaces will be given by translating down the infinity in such a way that for any n, Pn will be at H0. So the limit of this new sequence will be minimal surface that is tangent to the vertical cylinder above gamma at an interior point, that is the lifting of P at H0. Again, the maximal principle implies that the limit, the infinity, and the cylinder above gamma must coincide. But for the same argument as before, that is that a part of gamma lies outside T, these two surfaces cannot be the same, and this proved the result. The last argument left to explain before proving the theorem is the flux argument. If U is a Killing graph over a relatively compact domain omega, we call X of U the horizontal component on the normal metal fit to the surface times mu. Then we see that if the U is minimal if and only if the divergence of X of U is zero. So it makes sense to define the flux of U over a piecewise irregular curve gamma as the integral along gamma of the product between X of U and eta, where eta is the inner normal vector of gamma. Now, since the norm of X of U is smaller or equal than mu, we have that the absolute value of the flux of U over a curve gamma is smaller or equal than its mu length. Furthermore, the Stokes theorem implies that the flux of U over two homotopic curves has the same absolute value. Given this definition, it is not difficult to prove these two results. The first one guarantees that the equality is reached if and only if the gamma is a mu geodesic and the function diverges to infinity above it. The second result describes the property of the flux taking limit. So we use the flux argument to study the shape of the divergent set of a sequence proving the following result. So we take omega to be a Jenkins-Herning domain, and we consider on it a sequence of minimal solution that is decreasing, that is non-decreasing. We assume that for each open arc C in omega, we have that each U extends continuously to C, or the sequence and the sequence converges to a continuous function, or the sequence tends to uniformly to plus infinity. Furthermore, we denote by Bu the divergent set of the sequence. Hence, we have three results to prove. The first one is that the boundary of the divergent set consists of a finite set of non-intersecting interior mu geodesic chord in omega that joins to vertices in the boundary omega together with the mu geodesic in the boundary of omega. The second item to prove is that two chords in the boundary of the divergent set cannot have a common endpoint at a convex corner of the boundary of omega. And the last item is that a component of the divergent set cannot consist only of isolated point or interior chords. In this talk, we just give a hint to prove the first item, since the other two can be proved in the same way. We first notice that part of the boundary of the divergent set is also part of the boundary of the convergent set. So it is obvious that the boundary of the divergent set must be the union of homogeodesics. So to study the first item, we first see that that a homogeodesic in the boundary of U cannot tend in the interior of a mu convex arc. See. So we assume by contradiction that this happens, and we take 2 points in C that are sufficiently close, and we construct this Jenkins-Herring surface. The existence is guaranteed by the existence of shared type surface we proved before. Now, the maximum principle implies that omega plus is above any sequence, any element of this sequence. And so the monotone convergence theorem implies that this sequence converges in the interior of this domain with boundary the convex arc C and the mu geodesic gamma. And this contradicts the fact that the part of the boundary of the divergent set ends in the interior point of C. Now we want to show that the boundary of the divergent set cannot have vertices in the interior of omega. And we do it again by contradiction. So we assume first that the boundary of the divergent set has a vertex of angle smaller than P. In this case, we can proceed as before, and we consider a sufficiently small geodesic triangle such that the vertex of the boundary of U lies inside of the interior of the triangle, and the vertices of the triangle are in the convergent set. Then we consider as upper barrier this minimal Jenkins-Herring solution, and again by the monotone convergence theorem we have that in the interior of this triangle the sequence converges. And this contradicts the fact that the vertex of the boundary of U lies inside of the triangle. Finally, we assume that the boundary of U has a vertex of angle bigger than P. Then we consider again a sufficiently small geodesic triangle such that 2 sides of it are part of the boundary of U, and the other one is a geodesic, and we use the flux argument. Now, the previous two lemmas, we see in the previous slide, guarantee that the flux above L1 and L2 are exactly equal to the mu length of L1 and L2 respectively. And also we have that the absolute value of the flux over L3 is strictly smaller than the mu length of L3. Now, if we take the flux above all the boundary of the triangle, we have that this is 0. But this cannot happen because this path contradicts the triangular inequality. This last argument is what we are going to use to prove the theorem. Let us recall the statement of the theorem. We want to prove that if the family of regular curves is not empty, the solution exists if and only if these two equations are satisfied for every mu polygon. No. Let us recall the statement of the theorem. We want to prove that if the family of regular curves is not empty, the solution exists if and only if these two equations are satisfied for every mu polygons in the admissible Jenkins-Herring domain whose vertices are chosen among the endpoints of the mu geodesic arcs where the solution diverges. If the family of regular curves is empty, we prove that the solution exists if and only if the same hypothesis before is satisfied and in addition, the total mulem of all the AI is equal to the total mulem of all the BJs. In both cases, the uniqueness is guaranteed by a generalization of the maximum principle for minimal graph with possibly infinite boundary value. Since the proof is actually the same as the one of the previous works, I will not give all the details, but just the idea to solve each case. So, to solve the problem, we distinguish three cases. In the first one, we consider the family of BI to be empty and the function on the regular curves to be bounded from below. The same argument applies when the family AI is empty and the f is bounded above. We also need to assume that one of the regular curves AI has a strictly positive geodesic curvature at first, but this hypothesis is easily removable. So we start considering the sequence of minimal scaling graph with these boundary values. And with the same argument we used to prove the shape of the divergent set, we can prove that this sequence is uniformly bounded in the convex hull of the CI with strictly positive geodesic curvature. So the convergent set is not empty. What is left to prove is that the divergent set is empty. So suppose it is not, the lemma of the divergent set assures that any connected component of V is bounded by a geodesic polygon P with vertices among the vertices of the AI. So we consider the flux above P, that is zero for the Stokes theorem, and we decompose it in the sum of the flux above all the AI contained in P plus the flux of on what remains of the mu polygon. The lemmas of the flux argument implies these following two inequalities, which together with the first equation implies that gamma is smaller or equal than 2 alpha. But this contradicts the hypothesis of the first case of the theorem, and so we have the result. The next case we consider is when the family of regular curves CI is not empty, and we are not making any assumption on the set of BJ or AI. So we are again in the first case. Here we consider the sequence of minimal scaling graph with these boundary values and use the compactness theorem, taking as upper and lower barriers the minima solution with the following boundary values, whose existence is guaranteed by the previous case. The last case we consider is when the set of regular curves is empty. In this case, we are assuming that alpha is equal to beta. That is, we are in the second item of the problem. With this hypothesis, we cannot build the upper and lower barriers as we did in the previous case, since in this case, we will have that alpha or beta is equal to gamma over 2, which does not satisfy the hypothesis. So we consider these two following functions, omega plus and omega minus, and the idea is to build a sequence of minimal graph that is bounded above by omega plus and from below by omega minus, and such that this sequence diverges to plus infinity on all the AI and to minus infinity on all the BJs. So we start considering the sequence of minimal graph with the following boundary values. For any choice of n, we can take a positive constant C smaller than n, and we can divide the Jenkins-Henry domain in these two following sets. And each one of these is can be seen as the union of its connected component, such that every each AI contains the AI, and every FCJ contains BJ. The second hypothesis of admissibility guarantees that if C is sufficiently small, then FC is disconnected, and if C is sufficiently large near N, EC is disconnected. So we take M of N to be the sum of C between 0 and n, such that FC is disconnected. Since FC is open and its closure is obviously connected, then also E of M of n is disconnected. So now we define the new sequence of minimal graph, translating down each solution BU n plus of M of n. By construction, we see that for any I1 there exists an I2 such that the intersection of these two sets is empty, and such that in the first set omega plus I2 is above any one. The same is also true as an estimate from below in the f of M of n J1, J2. So what we have is that omega plus is an upper barrier, and omega minus is a lower barrier for our sequence. So what remains to prove is that this sequence diverges correctly to the on the boundary. That is, both M of n and n minus M of n diverges to plus infinity. We prove only the first case, since the other one follows by the same argument. So we assume by contradiction that M converges to M of n converges to a finite number M. Then the limit of this sequence is a Killing graph that diverges to plus infinity on the AI and to minus m on the BJs. Then we use the flux argument, and we have that since the solution diverges to plus infinity on AI, the flux above the union of AI is equal to alpha, and since the value of u in the BJ is finite, the flux above the union of BJ is in absolute value strictly less than beta. Since the Stokes theorem implies that the flux above all the boundary of the Jenkins-Herring domain is 0, we will have that alpha is different from beta. But this cannot happen since we are assuming for hypothesis that alpha is equal to beta. And the same argument applies for the other case. And this concludes the proof. We now see an example of a Jenkins-Herring domain that is not admissible, but on which there exists a Jenkins-Herring solution. We consider the Killing submersion with zero undercurvature and constant Killing left, where the base surface is isometric to this deformed cylinder of the Euclidean space. We consider on M the relatively compact domain contained between gamma minus and gamma plus that are two geodesics of the cylinder that are symmetric with respect to the geodesic alpha. In this case, we want to solve the Jenkins-Herring problem with values minus infinity on gamma minus and plus infinity on gamma plus. We notice that this domain is not admissible because the condition B of admissibility is not satisfied, since since neither AI nor BJ are disconnected. Nevertheless, in this case, we see we can solve the problem. We first notice that there exists a solution U to the Jenkins-Herring problem in the domain bounded by gamma minus and alpha with values minus infinity on gamma minus and 0 and 0 on alpha. By definition M, the reflection with respect to alpha is an isometry of M that can be lifted to the ambient space E. And since the van der curvature is 0, there exists a reflection with respect to the horizontal lifting of alpha in E. Using this reflection, we can extend the solution U defined in this small domain to all the initial domain, finding a Jenkins-Heller solution over a non-admissible domain. It would be interesting to find a way to prove the result without assuming the condition B as a hypothesis, but it seems impossible to develop a method to construct upper and lower barrier in this case. Indeed, all the examples known that do not satisfy this condition B are built using some symmetry of the ambient space. But let us see now a couple of applications of the Jenkins-Herring theorem. We consider first the Heisenberg group, that is a particular case of Killing submersion, where the base is the Euclidean plane and the van der curvature and the Killing length are constant. This last property implies that all the fibers of the projection are geodesics of the ambient space. So there exists a Schwarz principle proved by Sharp and Tobiana that can be applied in this case to all the graph which contains a vertical fiber. That is the case of a Jenkins-Herring solution with only divergent boundary values. So we can be complete shape type minimal surface diffeomorphic to the one of the Euclidean space over the same tessellation of the plane. The last application we see allow us to build non-proper embedded surfaces of the Euclidean space. We recall the description of R3 as Killing submersion with respect to the rotation, and in this case we have that the mu geodesics in M, that is the Euclidean half-plane, are of two types. The horizontal lines that rotating give the horizontal plane, and the catenary that are classified as a two-parameter family. So fixing a catenary and a parameter t of translation, we can tessellate M as follows. Notice that every tessellation on this kind depends on three parameters that are the two that describe the catenary and the parameter that define the distance between two catenaries. We can solve in each style of this tessellation the Jenkins-Herring problem with boundary plus and minus infinity as described in this picture. This because each tail of the tessellation is symmetric with respect to the horizontal line passing through the vertices of the tail. The natural question to ask in this case is that if for some choice of A, B, and the parameter of tessellation T, the solution on every two tails sharing a vertex can be stick smoothly. The answer is not trivial, since there is no Schwarz principle that can be applied in this case, since we recall that the vertical fibers in this case are the circles around the straight line of rotation. And with this application, I end my talk. So I hope you have enjoyed, and see you in the session of questions. Bye.